all in the technology world. 0% attrition. That must have been a pretty amazing company to work with. 0%. Here's the next. Speaks to my heart. 50% women. Woo. Yeah. We do not find that often, and we all know it, and it's a shame, and we're all working on it. And I ask everyone in the room to make sure that you're looking at gender diversity and other types of diversity across your teams. It is important not only for your business, it's critically important for your products. I'm preaching to the choir. You all know that. I just needed 30 seconds. As a 12-person startup, he beat out a couple of companies, including Facebook, in an international machine learning competitions, plural. He was the team, DLA. The company was the fastest growing company in Arlington by revenue 3 years in a row. And they, as I mentioned, they were sold and were acquired in 2019. And he wrote the machine learning strategy for an engineering directorate of about 7,000 engineers once his company was acquired. And I mentioned already that I've tried to get him to co-author a book with me, which we have literally blocked out the chapters. I just need to write it.
That was a private conversation.
Maybe the public encouragement to write a book. Please help me in welcoming my friend, someone I turn to often, data scientist, business executive, and not just my friend.
Okay.
Here, I'm gonna.
We're good. We're good on. This audio is good. Let's just don't sweat it.
Just this? Okay.
Yeah.
All right. I turned it on, so let me know if I should turn it off. Oh, you may have that.
Yeah.
It's good. It's looking good.
Let's see. So let's get out of this. And let's get this thing up here. It's all coming on now. Let's see. Is this us? And thank you, Greg Grosnitz, who also flew here this morning to be here, so thank you. And thank you, Jennifer Ives, like they said, connector extraordinaire. And thank you, Jennifer Ives, top 50 women top 50 leaders in SaaS. And if any of you want to get to know Jennifer Ives better, she just did a podcast with Trace Bannon called the Real Tech Founders Podcast. And I don't just recommend this particular episode because Jennifer's in it. Trace Bannon also recently interviewed Dr. Rebecca Bilbrow of Rotational Labs, and I recommend the whole podcast. So thanks again. The person that got us that Artistry venue that people remember in 2014, this is that talk. Jennifer got us that space. She was at Arlington Economic Development at the time. And at the time, it was the most attended data science event in the history of DC2, and you heard some people talk about the history. And that was good, but it was also bad because here's the fire exit, and here are people in the stairwells preventing people from getting to the fire exit. So we were lucky that there were no fire marshals at the event. And here, let's can we get a round of applause for Janet, Jeff Hale, and Dr. What do I gotta do here?
You're fine there. I think just lean in a little less.
All right, I'm gonna lean in less. But yeah, thanks, Janet. Also, let's thank Jim Eggenreiter of Virginia Tech. He joined Deep Learning Analytics for our species ID work with DARPA, and that had the best performing species ID in North America in 2018, but he's also just a tremendous naturalist. He was just named Career Tech Educator of the Year in the US. And one last person I want to thank, because they're also connected to Deep Learning Analytics, was Diane Murphy, professor at Marymount. She was an advisor at Deep Learning Analytics when we got started. And also I want to thank Tony Andrews. So she's not here tonight, she had a family thing, but in February 2017, she coordinated the first DC2 event here. Dr. Jennifer Sleeman, of an alumnus of Deep Learning Analytics, she gave a talk on GANs here. And that talk ended a year-long string of all-male data science DC talks. And that was, we know that because Kate Rabinowitz wrote this post for Data Lens DC, where she made that point. And all of those people that I just mentioned, so Dr. Jennifer Sleeman, Dr. Rebecca Bilbrow, and Kate Rabinowitz, they were all named best data scientists in the DC region by DC Femtech in 2017. Okay, so this is the title of the talk, How Attention in 2017 Got Us ChatGPT, Historical Perspective on the Attention is All You Need paper. So the Attention is All You Need paper came out in 2017, and it introduced a technology called the transformer architecture. Now, we're in 2023, and people seem to only recognize ChatGPT as our Lord and Savior. But that is the heir to that 2017 paper, and I'm going to talk about the history between those two. So a few disclaimers before we get started. I have to say this because I could just be shilling for these companies. I will shill for NVIDIA. So I own stock in NVIDIA, Microsoft, Google, Facebook, and Amazon, and you might also want to own stock in NVIDIA. So let's start with the end here. What is ChatGPT? ChatGPT is what's called a large language model that responds to text prompts. And why do we care? Because chatbots have been around for a long time. And even if you don't care about ChatGPT, why is the media all worked up about it? And I'll start with the media attention, but the key bit is that the transformer architecture is the technology inside ChatGPT. And if anyone was waiting to see if transformers would catch on, they've caught on. So here's news stories. Here's Reuters talking about ChatGPT getting to 100 million monthly active users in January, and it was released just 2 months prior. That was the fastest in internet history. And here's a Bloomberg article talking about using ChatGPT to predict Fed rate moves. And here's a New England Journal of Medicine article talking about using ChatGPT in medicine. And here's a CNBC article talking about Google updating its business model to respond to the threat from ChatGPT to its search business. And that is frenzied media attention. So quick show of hands in the audience. Does anyone remember something called DALL-E? Oh my God. Okay, so I guess yes. All right. So DALL-E, if you remember, that was in June of 2022. You would type in a text prompt and it would draw something for you. That's this right here, and that was a big phenom. But here we are in December of 2022, and you can see what happened. I just discovered the pointer. And I can only show you this much because if I show you any further, this just goes so high that this thing disappears. So now I'm going to compare ChatGPT and GPT search volume to things that are maybe more commensurate. So here I have HBO's hit zombie thriller The Last of Us in blue here. And here is Biden in purple. And you can see ChatGPT and GPT are more consequential search terms to the business press than either of these two. And this is also historic media coverage. So here's a media cloud chart where you basically see no search volume for ChatGPT right before it launched, and then all of a sudden you see this happen. And it covers things like in March, the Bard being released in the UK by Google, and in May there was the AI testimony to Congress. And thanks again, this is another Deep Learning Analytics alumnus, Paige Gully. She pointed me at this chart. So is it all hype, or is there actually any kind of market response to ChatGPT? So here's Forbes, and they say there's a hot new job that pays 6 figures. It's called AI prompt engineer, and prompts are the text you enter to get something back from the ChatGPT. So if we look around here for prompt engineering jobs, what do we find? Well, here's one, and it is 6 figures. And what do they want? They want 1 plus year of experience. This was when this role had existed for about 6 months. So in the near future, I do expect type A HR departments to recruit senior prompt engineers with 3+ years of experience. So what are large language models? They take some sequence of objects, typically words, and produce as output another sequence of words or just more words. And what's common to virtually all of them, transformers, that's the architecture. I'm going to talk about tonight. That paper that I mentioned, they called it attention is all you need, but attention is just part of the transformer. You need a lot more than just that. So because there have been 6 years between that paper and 2023, on the next slide I'm going to give you a very incomplete chronicle of prominent named AI models based on the transformer. And you'll notice that there are a bunch of Sesame Street and Transformer names like Elmo, Bert, Ernie, Big Bird, Grover, Kermit, and Megatron there. And that's because the very first one of these that was really popular was this thing called Elmo, and the L stood for language, the M stood for model, and everybody loves Sesame Street, so that's how that happened. But here are all of these models. This is GPT-4, the most recent, but you can see this chronology. There are lots of different organizations training these. The logo next to each named model is what organization trained it. So for instance, Microsoft, Google, Baidu, OpenAI, for instance. But I'm going to go back to 2017, and this is what I'm going to talk about tonight, that transformer architecture as it existed historically in 2017. So what is it? It takes an input sequence of words, I say tokens here, goes through something called word embeddings. I'll talk about what those are, both on the input side and the output side. It was a translation model. Then goes through something called positional encodings. Then does something called multi-head attention with masking. I'll talk about that. Then goes through feed-forward blocks. Then there are these blocks called add and norm. And then there's a linear layer output and a softmax. So that's just introducing what it is. And now I think I can move this slide forward. Okay, so that is now the, oh wait, I have to go here. So this is their figure 1 from their paper, and this is what I just described over here. I'm not making any of that up. That's all right here. So before I go into, let's just talk, okay, because some people here might think I'm going to talk about AGI, but I'm not going to do that. So tonight's talk is a historical snapshot of the transformer architecture and some perspective on it. It is a brief visual walkthrough of each of the components, and it is some recommendations and pointers to other resources to help understand that specific architecture. It is not, tonight's talk, a discussion of DALL-E, ChatGPT, and other recent models that have, quote, captured the imagination of the media. It is not a comprehensive taxonomy of LLMs. I don't even know where you could get that because there's so many LLMs out there and there's more every day. It's not a discussion of ChatGPT business models, but that's super important, especially to startups. I'm sure Jennifer is well aware of that. And it's not a discussion of AGI. AGI is artificial general intelligence, and it's not a broader, more in-depth discussion of deep learning than appears in that 2017 paper. So how do I know people want transformers explained? The top search result is attention is all you need explained. So, I know that this is something that even if you don't want to own up, people want to hear how this works. So before I talk about transformers, let's talk about what happened before transfer. How do people turn sequences into other sequences before they get transformers? And there were two model types. The RNN is the more general type. That means recurrent neural network. And the LSTM is basically a model. LSTM is long short-term memory, and what that does is it propagates this hidden state, and that seemed to help, but it still didn't make modeling sequences work really well, or at least not as well as people wanted. So no matter how you tried to patch this, it always had trouble because there was just this hard-coded connection between taking the last state and then the past words. These are the input word sequence, where T is the position index in a sequence, for instance, and these are the output tokens. But there was always this hard-coded computation of the next token from the state and the past inputs, and that was its problem. And for that reason, it could not do a good job on long sequences. It had a hard time keeping things straight in its memory and keeping a sequence coherent. And so what was the answer to that? The transformer. So before I talk about any individual piece of the transformer, you're late, David. I'm going to first just talk about the deep learning, the ML themes in deep learning and machine learning that the transformer architecture grew out of. And so what themes are they? There's deep learning, regularization, NLP word vectors. NLP means natural language processing. And something about presenting your results. Train first, then interpret. And then also some empirical evidence that self-supervision helps. So in deep learning, what were the themes that this paper inherited? They weren't new to the paper, but this paper did use. One is they trained on GPUs, and that was mainstream since the 2012 AlexNet Big Bang. Also, that deeper models outperform, and that was also mainstream since 2012. So what they did is they layered their encoder and decoder layers into a deep network. They also trained models with fewer and more parameters because they knew that bigger models would outperform typically. Also, the dividing line, well, it's not really a dividing line, but culturally, after the deep learning revolution, the community was more open source, and they did release their code open source in 2017. And they also used large, open, train and test data sets that were available to everybody so you could reproduce their work. And they did get a state-of-the-art result on a relevant task. They did machine translation. And they also did a bunch of other technical things, like label smoothing, dropout, residual connections, layer norm, and they used the atom optimizer, and they used rectified linear units. Those kind of were popular since 2010. And I'll go through these very briefly next. So the ResNet architecture. So typically when you compute a neural network, there are a bunch of layers, and any individual layer has some output X, and it goes through some layer and produces some F of X output. What they showed in the ResNet paper, and ResNet was just short for residual connection, residual network, was that if you then added a copy of the input to the output computed from that input, that would make gradients behave better. And that basically made these things easier to train. So that's a kind of regularization. So before the ResNet paper, you wouldn't see this, but after the ResNet paper, you would have this magenta connection. So now in the transformer architecture, when you see that, I copied that motif here on the left, and here's the transformer architecture on the right here. And so you can just see how it inherited those motifs in these add and norm blocks. Other regularizers, Atom. So Atom, whenever you have a neural net optimizer, you have to say which one you're going to pick. Here are a few different options, and here is Atom, and you can see it gets to a better optimum faster than competing approaches like Eta Delta, SGD Nesterov, RMSProp, Eta Grad. There's nothing hard and fast about this. Sometimes others win, but it's just a good bet, Atom. They also use the regularization technique called dropout, where every time you see a new training example through the model, you don't use the whole model. You just turn off, say, a fraction of the weights and compute the output. And so that also helps regularize. They also did something called label smoothing. So usually when you're training a model, you have something called a one-hot for your labels. And what that does, it has all the probability that that thing is that label at one category. What label smoothing does, it takes a small amount of label and spreads it to all the other categories. So they use all these regularization techniques. Since the AlexNet paper from 2012 is arguably the big bang for computer vision and deep learning, and the 2017 paper could be considered a similar big bang for natural language processing. I wanted to compare them. So the first thing is that there were learned specializations. And so here you see all of the first layers. There were 96 filters that were learned in the first layer of AlexNet. And this was not programmed in. These were all initialized as random noise. And then by showing them millions of images, it said, oh, well, these are good patterns to help recognize what objects are. And similarly, the attention is all all you need paper, they learned attention heads that get initialized as random things, but then by the time it's done training, they're doing grammar things, and you can actually see what grammar things they're doing. They both used millions of parameters models, so not billions of parameters, and also not smaller models. And there was 62 million in AlexNet and 65 million in the base model of the attention is all you need paper. And this could be a coincidence that they were so close, but I think what this lets you do is lots of experiments with a base model to kind of pick hyperparameters. They both took on the order of 10,000 dimensional inputs. So AlexNet took an image that was 224 by 224 by 3 RGB values. That's about 15,000 dimensions. And produced a category out of that. Every token, they used about 40,000 tokens in their vocabulary and attention is all you need paper. That would then produce a token output. Those are both about 40,000. The compute time, so it took 6 days of computation for AlexNet to get a state-of-the-art result, and the attention is all you need paper took about half that time, but they also used 4 times as many GPUs, and the GPUs were a lot bigger. I think there were 22x the amount of GPU memory and 28x the GPU cores. So it's not apples to apples, but it was a relatively quick compute. We all do think that 6 days is a quick compute, right? But it certainly is not the 90 days that it took to train ChatGPT on 25,000 NVIDIA A100s. It's not that. They also both said that more compute would help, and they also said that unsupervised pre-training would help. And they both papers turned out to be right about both those things. So another thing that was happening even before this paper, but definitely this paper did the same thing, is first they learned a representation of their attention heads that got a state-of-the-art result. And state-of-the-art here just means the best known result in the world on a public data set that could be reproduced. Then once you have that, then go and try to show people how it works. Don't do it the other way. Don't start with an idea and say, oh, my idea is so great, I'm going to show the world how it works. No one cares until you get this. So they did that sequence. So that happened in the Google Brain cat detector work from 2012. There they trained on millions of YouTube videos, and then they looked at the network and they said, well, what was it learning? What does it respond to? Well, one neuron maximally responded to that thing, and the New York Times covered it because that was crazy. That wasn't programmed in. It just learned that YouTube was full of cats.
That's not wrong.
And at the time, that was also one of the biggest networks ever trained. So there was a machine translation result that used something like Word to Vec in 2013, and here on the left, you see what they learned. None of this was programmed in, but on the left are word vectors. So a word vector is basically a vector that represents a word, and you can project it down into a space that we can see, like 2 dimensions, and then look at where the English vectors are compared to, say, the Spanish vectors. And so just these, for instance, 4, 5, 3, 2, 1, you can do a linear transformation of both of their learned spaces, and they line up. That was new and interesting and motivating and useful as well. And the attention is all you need paper. This is from their appendix. Once they got that state-of-the-art result in translation, they then said, well, what do these attention heads do? Well, this attention head says law should pay attention to the words the and law. These perfect should be perfect. This one will pay attention to but. These pay attention to other things. So these are specialized attention heads. You can't always say what the attention heads are doing because they all work together and there are hundreds of them. So they might be doing parts of tasks, but on the left that might be noun phrasing, but I'm not good at English, so. So another thing that they inherited was word vectors. And so this is the Thomas Mikolov paper in 2013. And here on the left, you can see, so a word vector. You represent a word by some continuously valued vector. So here is man in 2D, here's woman in 2D, uncle in 2D, etc. And once you represent these things as vectors, you can start doing math on the vectors, and you can find that the vector difference between man and woman is about the same as the vector difference between uncle and aunt, and that's about the same as the vector difference between king and queen. That's interesting. That was not programmed in. That was just learned from lots of Similarly, on the right here, you have king and the plural kings, and queen and the plural queens, and that was also not programmed in, but now you could guess. If you didn't know the plural of a word, you could just say, oh, well, what's the distance to other plurals, and guess that the word closest to that will be the plural of this word. And the attention is all you need paper use those word embeddings. So another thing that was in the water, part of the machine learning sort of state of the art at the time, was self-supervision. So in self-supervision, you train a network to do something useful. On the left here is something called in-painting. So you're given this image, and you don't give it these pixels of that castle thing, and you say, learn to fill that in. And if this is what you get out, great. What that ends up doing is, one, giving you labels for free. You just take an image and take a part out, you make it learn that. You didn't have to have someone hand label that data. So it was a great way to get lots of data for free. And once you know that a model is doing a good job on these, what are called pretext tasks, they're typically good at doing other machine learning tasks too. It's learned that vector representation of things that now you could probably do a good job of training object recognition on very little data once you have that working. Very little label data, I should say. And similarly, fill in the blank is the same kind of objective that you used in training a transformer. Fill in the blank type thing. So here you get the words the, quick, and you don't get this word, and then you get fast, and it has to guess what's this word. So just like in computer vision, if it does this well, if this can do this well, that means it's probably learned a good vector representation of things to do other tasks. And that's what we find. And that is all I'm going to say about the machine learning context that transformers grew out of. That was not new. All that stuff pre-existed, the 2017 paper. And even the other stuff arguably is parts of things that are also already existing. But let's start with the input sequence. Here we are. How do they represent words? So they use something called byte pair encoding, and I'm going to talk tonight mostly about word tokens, because word tokens are just easier to draw visuals for. Byte pair encoding breaks words down into pieces. So here is byte pair encoding. Here, the corpus that's being encoded, just a toy corpus, and it has these words: hugging face, hug, hugger, learning, learner, learners, and learn. And there are lots of repeated subwords in there. So what byte pair encoding does is it tries to find the things that are redundant and represent them as units rather than individual pieces. So there are 3 steps to byte pair encoding, and this YouTube video, she does a phenomenal job really concisely and clearly describing how all this works. But you start by initializing as just the letters that you see in the corpus. Then you put all of the pairs of letters that you see in the corpus into a big table, and you see which pairing of letters happens most frequently. Then you take that and you merge it. So L and E will get merged into LE. Then you add that to the list of tokens. And then you just repeat, lather, rinse, repeat. And after 8 merges, this is the vocabulary you'll have, and this is how you would represent the corpus. So that's byte pair encoding. Please don't disappear. All right, word tokens. So I'm going to talk about full words. So that broke words into pieces. But I'm going to use a dictionary of full words, and I'm going to use one-hot encoding. So what's one-hot encoding? Here is a 29 by 29 matrix. One-hot just means one value is 1, and everything else is zeros. So here on the left, I have 29 words. These, the, its, hers, his, pet, dog, cat, horse, cow, wolf, tiger, wags, bark, meow, purse, his, house, tail, mean, hoof, paws, leg, foot, person, loud, quiet, fear, and peace. That was my patter part of the evening. And so the first word would just be represented as a 1, followed by all zeros. And then the next word, the, would be represented as a 0, then a 1, and then all zeros. So what I've done is I've just taken these words and made a one-to-one mapping. That's the word tokens. And that's what go in. Then word embeddings. I just talked to you about them in terms of the Mikolov paper, that it turns a word into vectors. That's this step. So you take those tokens in, and I'm gonna visualize them in high dimensions, because typically word embeddings are on the order of hundreds of, like, somewhere between 300, 500, 1,000 dimensions maybe. And we want to be able to look at them, so I'm going to compress those down to 3 dimensions, just so you can see them. And I'm also going to talk about how token similarities with dot products end up putting words that are used similarly or have similar meanings together. So here are word embeddings. Here you have the same words, but now you have different vectors. So this vector, and I'm going to develop mostly the base model in the attention is all you need paper, and that use 512 dimensional word vectors throughout. So there are 512 numbers here, and now they're not just 0 or 1. They could be -2.7, 1.2, 0.5, whatever. So the shade of blue here determines what the value is. But we can't see these in as humans, or we can't see in 512 dimensions. But the thing that these word vectors do is they put things close in that high dimensional space that are either used similarly or mean the same thing, or mean similar things. So let's just use principal component analysis. This is a dimensionality reduction technique. So now we're going to look at them in 3D, so now you can see where words like cow, horse, wolf, pet, tiger, and cat live in 3D. So now we can see them. Here is what that corpus looks like now, not as 1-hots, not as 512, but as now 3D word vectors. And the hope is that dimensionality reduction, that dimensionality reduction, that's deep learning analytics alumnus Aaron. I guess that was approval.
Yeah, it's good.
Should I move that? Oh, I should move this over here. Sorry. Sorry, I should have been doing that. Am I on that? I am still on that. Okay. So here they are in 3D, but let's look at them in 3D. Here they are. Here are all those words in 3 dimensions. Now we can look at them. But I want to show how the dot product similarity is reflected in here, because dot product similarity ends up being important in the transform architecture. So this is dot product similarity. So what's a dot product? A dot product is, if I have 3 numbers in each vector, I multiply element by element, the 3 numbers with each other, and I add them together. That's a dot product. So here are normalized dot products, but I'm just going to call them dot products. And you can see some structure along the diagonal here. This is where words have some high value with respect to other words in that block. So if you just look at these 2 blocks, you can see that these words here are basically 4-legged animals: pet, dog, cat, horse, cow, wolf, and tiger. And this block looks like these verbs: wags, barks, meows, purrs, neigh, howls. So what it really looks like is these are nouns that correspond to 4-legged animals. And you might even infer that because the word pet's in there, that the corpus this was trained on, maybe most of the pets were 4-legged animals. And here are the verbs for animals, but all of these are animal words. And down here, this is tail, mane, hoof, paws, leg, and foot. So now let's look at these in 3D. So here are all those animal words, all of the things in that green dash box. And here are pet, dog, cat, horse, cow, wolf, and tiger. They're here. So that's like its own little cluster of words that either mean similar things or use similarly. Here are indoor domestic animals: cat, dog, and pet. Here are outdoor domestic animals: horse and cow. And here are wild animals: wolf and tiger. Here are parts of animals: foot, tail, hoof, mane, paws. Here are animal sound verbs: meows, purrs, barks, howls, and neighs. Here are all the animal verbs I put in there. So those include wags, which isn't a sound word, but it also includes paws, which is a verb, but it's also part of an animal. So you can see how they overlap. So the space has to learn to do things like that too. Here are all the sound words, and some of them have nothing to do with animals, like loud and quiet here in red. And then there are other words down here like its, these, the, his, etc. So those are how word vectors work. Good?
That's nice.
Okay. I'm just going to cross my fingers. If that's okay. So then they did something called positional encodings, and that's this right here. And there's a little yin-yang symbol, and I'm going to go through the intuition for that, but in 3 dimensions rather than the hundreds of dimensions that they used for their word vector. So here's a little yin-yang symbol. Looks like a little sine wave, so let's take the sine wave. And they wrote, in this work we use sine and cosine functions at different frequencies. And then they had an equation, let's just ignore that. Let's make this an actual sine wave instead of sine motif. Let's make position the index of the word in a sentence. So this would be the first word, second word, third word, fourth word, fifth word. And what we're going to do is perturb each word a certain amount by their position. Oh, they also said we use sine and cosine, so there's a cosine. But they also said of different frequencies, and here's a slow sine. So we'll assume that we have 3D word vectors, and these are the things that are positional encodings. So imagine we have a word vector location like I just showed you. If it's the first word in a sequence, it gets perturbed by this much because you look up on the orange vector that value, you look up on the green vector that much, and you look up on the blue vector that much, and that's where that gets perturbed to. If you go over to the second position, you get perturbed that much, third position that much, and you can paint out shape. And in 3D, we can even name that shape because it's just a cosine, a sine, and something that looks like a ramp, and that means it's a helix. So that's what these positional encodings look like. So now if we take those 3D word vectors and say, well, where do they move to based on their position in the sequence? These are all the places that word would move to, these are all the places that would move to, and all of them can be moved to different positions. So, all right, let's do an example sentence. It is the dog wags its tail, so the word token sequence is the dog wags its tail. So those words in that corpus, that was index 1, 6, 12, 2, and 18. So if you wanted to represent that as 1-hots, here it is. And then if you map that through the word embeddings, here are the 3D versions of those. And here is that 3D plot. And there are now 5 vectors here that correspond to these words. The problem with this representation is the dog wags its tail would be represented exactly the same as the tail wags its dog, because the same vectors. So that's why we have these positional encodings, to move things a certain amount. So here are now these little helices, and let's add the perturbations to each of these vectors. That's the first word, second word, third word, fourth word, fifth word. But we don't keep the whole helix, we just keep where they move to. So now it's these 5 vectors, 1, 2, 3, 4, 5. Where there's a number inside each of these, that's the position of the sequence and how much you perturbed it by the positional encoding. So that is through the positional encoding what we get. And that's the input to the rest of the transformer. Oh, nope. Okay, so now we're about to go into multi-head attention with masking. This is the heart of the transformer. They named their paper after it. It must be important. So I'm going to show you 3 things here. The first is that attention, as they define it in the paper, is like a Python dictionary lookup. And I just did a lightning talk on this a few weeks ago because I thought that would be something that maybe wasn't clear from first reading the paper. Then I'll also show how really that Python dictionary lookup isn't a lookup, it's a similarity-based lookup. And then I'll finally talk about how attention has learned to specialize. So they have this section called scaled dot product attention. And then they have this equation down here, and they don't say what Q, K, and V are intuitively. They just say they're matrices. And this is an equation. The Q matrix times K transpose divided by square root of dk, which is just a scalar. You take the softmax of that, and then use that result to weight all the values V. That's clear, right? So anyway, so that's why the lightning talk happened. So here is a Python dictionary that hopefully all of us here can understand, even the people who do are. So here is the query. This is just the string added attitude, and this is the input-output relationship I'm going to show equivalence to. So this is KV-DIC for keys, values, dictionary. The keys are cat, medicine, taste, attitude, and disposition, and they map to the values jinx, mad, better, bitter, yes, and fickle. So if you said KV-DIC of Q, that would be yes, because the word attitude maps to yes. That's the input-output relationship I'm going to show equivalence to. And to do it, I'm going to first develop some one-hot vector mappings. Oh, I'm going to only show you slides here. The talk from the other week has code, Python code, if you actually want to see the Python code for this. But K1 map just maps from the keys to their one-hot mappings. And V1 map goes from the one-hot back to the values. So the first thing I did, so what I'm going to slowly do, not slowly, it's pretty quick, is take that Python dictionary lookup and turn it into that equation. So we're not at that equation yet, but we're going to start by just introducing some vectors. So now I've made the query a one-hot, which is really just the one-hot mapping of the original query attitude. And I'm going to map all of the keys to their one-hots. Well, if you look at K1V-DIC of Q1H, it's still yes, because that maps to them.
Yep.
That's the same input-output relationship as before. But now because I have vectors for both the queries and the keys, I can now do math on them. So I'm going to do dot products because that's what the attention paper does. I'm going to take a dot product of every query with every key, and I have one query here, and the only place that dot product is non-zero is here. So the dot products are zeros, 1, and 0. If I then say, give me back the value where the max happens, that's all this means, this argmax of I, Qi with K1HI. That basically just says, find me the max dot product and give me the value. That's that. That's the same input-output relationship. Now I'm going to map the values, and then once I get the value out, which is now going to be a one-hot, I'm going to go back through that V1 map to get the answer out. And this again finds this one-hot and then converts it to yes. Aaron, you look like you're checking my math. Are you actually error checking my Python?
No, my foot is like, it's got a cramp.
Because this actually won't work because there aren't commas here. I thought there was going All right, so that was all picking a max, and so picking a max will do the same kind of thing. We just take one value, right, from the values. Now what I'm going to do is weight them. I'm going to take a linear combination of everything on the right here. And that could all go wrong because now I'm going to mix all these things together as a linear combination, and then that might not even go through V1 map. It might produce an error. But because they're one-hots, only one value gets a 1, all the rest are 0, so when I weight them, it's equivalent to an argmax. So this I can do. But now I can turn this into math. And so this is that math. So now I have Q1H. Now I've constructed a matrix K, which is the matrix in their equation 1, and K is there. You got to turn on its side, and you Q1H by K transpose. You divide by square root of dk, and then you multiply that by v. So this is not exactly the same as equation 1 because they had a capital Q, which just means multiple queries. This is just one query, and they also had a softmax out here. But this still has the same input-output relationship, and we're pretty close to equation 1. Here's equation 1. So now I've taken the one-hots for every one of the tokens, every one of the keys, cat, medicine, taste, attitude, and disposition, and now this is the matrix Q with multiple queries. This is the matrix K, this is the matrix V. I'm going to use dk equals 0.001. I've now put the softmax back in, and now it's Q, K transpose, divided by square root of dk, multiply that by V. Even if you're not following this part, you can just trust me that this equation is equivalent to what I showed you, to 9 decimal places. And if 9 decimal places is enough, we should talk about that at liberty. So here is the input-output relationship of the equation 1, where this is the original Q, cat, medicine, taste, attitude, and disposition. Those are the inputs. The outputs are jinx, map, bitter, yes, and fickle. You go back to the original KV dict. The inputs are cat, medicine, taste, attitude, and disposition, and the outputs are jinx, map, bitter, yes, and fickle. QED. Okay, so one-hots are mutually orthogonal, meaning they don't know anything about similarity. So they're really not doing the things that we know work. Oh no, oh no.
You got one of the two. Still.
I can't just give a speech.
Ah.
There you go.
What's happening? So they're mutually orthogonal, so they don't have that property of things being close to each other. And we know that the word-to-vec embeddings put similar words in similar locations, where words that are used similarly or are similar in meaning will typically have vectors that have high dot products, and then words that are unrelated will have negative or zero dot products. So what dot products will do is rank the relevance, not just pick them. And if you only keep the top handful of weighted values, that's what we call hard attention. And if you take all of them, like I just did, that's called soft attention. So one quick thing here, you see how this matrix V, or where is it? Here's matrix V. If the attention result looks like V, it's doing the same thing as the one-hots did. And when you define this as Q, K, and V, this is what attention looks like. And it looks similar. So like it has bright spots in the same place. It has dark spots in the same place. So it's not that all the intuition goes away, but it's just, you can't think of them as one-hots. Okay, so now let's go back to their paper, and this was their diagram in their paper, where this is just a block diagram of their equation 1. So the only thing that's different from what I showed you is this matrix M, and that's what's called the mask. And in their model, they had a mask on the encoder and on the decoder. In the encoder, the mask is just identity, so it goes away, it just disappears there. And if you're in the decoder, it's autoregressive. So it has to use a special matrix. This is that matrix. You don't need to worry about it, just know that it gets multiplied in there. So this is mass dot product attention. Let's use that as the icon for it. And oh, one thing. Attention had no learnable parameters. We just took the QK and V and computed it. Right? There's nothing special learned there. That's super important. I think some people think that attention has parameters. It doesn't. But now if you take the dog wags its tail, these are the position encodings, and then if you take the attention on those position encodings, you get these gray squares. There were no parameters that were needed to learn where those gray squares come from. But now let's talk about an attention head. An attention head now has learnable parameters. Those are these WIQ, WIK, and WIV. So now we're gonna transform the K, Q, and V's by these learned weights. We're gonna initialize them with just noise, but then as this thing learns, it'll learn to do useful things with these. So now we do have learnable parameters for each attention head I. So how do we do multi-head attention? We have more than one attention head. So here is the attention head, and we're just gonna make 8 heads here, and now they all have their own sets of parameters, and they compute these attention heads out. These are these amber and brown vectors. We put all those vectors together into one big vector, then we multiply by another weight matrix called WO, and that's what multi-head attention is. They name their paper this. So this introduces H sets, so for every head you get WIQ, WIK, and WIV, and then you get one of these WOs for every one of these blocks that you see. So now here's an example sentence. Let's look at the word dog. So dog, the original triangle is there, and if you say, okay, it's the second word, so let's go to the 2 that gets perturbed to. The attention head is there, but we don't really use that. We use these blue stars. So what this lets attention do is move words around to multiple places in its learned vector space so that it can do a better job at its task of predicting the next word. That's all attention's doing. Yes, each attention head has a specialized function. So now this is some of what they visualized as output of a particular attention head. So now you can look at any individual word and say, what other words in a sentence is that word paying attention to? So here the sentence is, the animal didn't cross the street because it was too tired. And here you have an orange attention head on the left and a green attention head on the right. And the word it by itself, if you just had to learn a word vector for the word it without the rest of the words, you wouldn't be able to say what mattered. But attention heads learn to do things with that. So here it said it, through the orange attention heads, that focuses on the animal didn't. So that looks like it might be subject, co-reference, or co-reference means what do pronouns point at, approximately. And here it was pointing at the subject of that word it. Here, the green one looks like it's pointing at what's describing the word it, because that's where those attention heads are large. So that specializes in co-reference resolution of predicate adjective phrases, I think. So what does a multi-head attention block look like? Here it is. It has all these learnable parameters, and this one up here, and let's just make it that. And here's where it goes in the encoder on the left and the decoder on the right. And like I said, use m equals I on the left and that other autoaggressive one on the right. Good? Okay, we're more than halfway through the transformer now. So now these feed-forward blocks, those are these two, and I'll do this. And so they called their paper "Attention is all you need," but more than 30% of the parameters were in these feed-forward blocks, and so you can't just take these away. If you take these away, performance degrades. So attention is not all you need. So here are those blocks. So they had weights and biases in their original paper. More recent versions have typically dropped the biases, but it's really just a 2 layers, and they had 2,048 parameters per layer, and since you had 512 dimensional inputs, that's 512 by 2,000, so on the order of 1 million dimensional parameters here. So for every feed-forward block, that's what you add, and here they are. Then the add and norm parts. So there are 5 of these. Those are these things, and remember I mentioned that those were those residual connection motifs. So here is, so the residual connections is just the add part. But the norm, what do they use for norm? They use something called layer normalization. And here's a paper that describes it, and it's got Jeff Hinton as an author, so that means that you are always allowed to cite it. And here's the more common batch normalization, C by N by number of tokens, per example. So what batch normalization does is it normalizes over the examples in a batch, and the layer normalization normalizes over the tokens in the example. And that is layer norm, and that's there. And now the last 2 blocks, linear and softmax. So the linear block just converts, this is a 512 dimensional vector coming out here, but out of the linear block you have all the tokens. And remember, there are 41,000 of them. So first you go to the token space, and then the softmax just computes probabilities. So this is what that looks like, and since there were 512 dimensional word vectors going into that last block, and there were 41,000 tokens, that was on the order of 21 million learnable parameters. And then the softmax these are scores that come out of the linear layer, and the softmax just converts those from 0 to 1 in probability. So if you look here on the left, that would be, for instance, the probability that the word was, say, aardvark, the first word in the corpus. And over here, this would be the probability that the word was, say, Zulu, the last word in the corpus. And those go up here, and we're done, right? No. So they also did not talk much about how this thing was wired up. So in the deep learning themes, I did mention that deeper architectures outperformed, and they did stack their layers. So in their base model, they stacked 6 of their layers together, and I'm gonna show you that. And they didn't really talk about how it was wired up in the paper, but they did in the code. And so this is how it was wired up. This is the encoder, so this is the first layer of the encoder, second, third, fourth, fifth, sixth. And down here, this is the decoder. So they had a machine translation model where they would put in, oh, they didn't do this, sorry. They would put in the source language here, and they would get the output language here. And one thing that you see is once it goes through and computes the first token on the translation, it then feeds that back as part of what it uses for predicting the next token. So it's autoaggressive. So that's why we had that M look different on the decoder. And let's go to, all right, so this they did not give you in their paper. So they do have a table 3 that says how many parameters were in each of the models they trained, but they didn't give you an equation, this equation. And thank you, Aaron Schumacher, down here in the front row for putting this equation together. They had a base model, like I said, every one of these arrows carries a 512 dimensional vector. Then the number of tokens was 41,000. There were 6 layers. There were how many units were in each feed-forward layer, 2,048. There were 8 heads, like I showed you in the multi-head attention block. And then you have a choice of how big you're going to make the keys, values, and queries, and they chose 64 for the base model. So when you look at their base model and you look at where they chose to allocate their parameters, 19 million in the attention heads. And yet, attention is all you need. It's not true. It's not true. There are more parameters in the feed-forward blocks and in the linear block than there were in the attention block. So anyway, attention is not all you need, and now that I have beaten that dead horse, that attention is not all you need, are we done now? We're not yet done, but we are almost done, honest. I will stop talking soon. What do all transformers have? These pieces, and typically wired up something like this, but not all of them will have the encoder and the decoder like the attention is all you need paper. That paper had both because it had a source language and a target language it was trying to translate to, so a machine translation. Some just have decoders, like all of the GPT models, they're just pre-training a decoder. And some just have encoders, like BERT. And there are a whole bunch of other types, and here is a family tree. This is the vanilla transformer that I was talking about back in 2017. But as you can see, I think I said this earlier, they've caught on. These are the GPT model, GPT family of models, and they include all the GPT ones, but also Chinchilla, Sparrow, Dolly, which is commercially compliant, for instance. Green is the BERT family of models. Here, VIT, these are vision transformers. You can do transforms with more than just words. You can actually use pixels. And there are a whole bunch of other families here. And one thing about this paper, I don't know if it's criticism, but I didn't find a legend for these colors. So this I worked with another deep learning analytics alumnus, Sunita Clark, and she was good enough to put together this by looking at their big table of all their models. So thank you, Sunita. Okay, now once you have the architecture, you have to train it. So all I've done so far is that all these weights are random values, but now you have to actually learn them. So that, like I said, they used Adam to predict the next word in sequence, and you just adjust all of the parameters so that words that you see happen in real life or in your training are more probable, and sequences that don't happen in real life are less probable. So that was 6 years ago. So let's go to this paper from a few weeks ago. This is now all that was described in the 2017 paper. It's just pre-training. Now they do other things called fine-tuning and human feedback. I have a feeling maybe Prima Roman might be talking about fine-tuning open source models in the near future, but I'm not going to talk about that tonight. This is what they did in the Llama 2 paper. So the Llama 2 paper, they took in 2 trillion tokens. Those are just sequences of words, so think of it as the pile of the internet. They did something called self-supervised training, which is exactly what I just described with Adam. And they produced something called Llama 2. And I'm going to call that a foundation model. And loosely speaking, a foundation model is a model you will never train. You are not going to train a foundation model yourself. And why? Because to train those, Facebook spent about $20 million to train all 4 of their different size LLMs. And just for their biggest one, they spent $10 million for their 70 billion parameter model. That was 3.3 million hours of A100 80 gigabyte GPU compute, and that's equivalent to about 539 tons of CO2. And if you have those kinds of resources and you're in this audience tonight, we should talk. So another thing that I mentioned in the deep learning themes was that bigger models outperform, meaning that if you have more parameters in a model, they would typically do better. They did see that with their bilingual evaluation understudy scores. If you had a bigger model, it would typically have a better score. And that has helped, but it's more than just the number of model parameters. It's also if you give it more data. This was true of deep learning for a while now, that more data makes things perform better, and if you train more, it'll also be better. Bless you. So these are so predictable now that they're called scaling laws for these large language models on how well they'll perform. This was an OpenAI paper, and they wrote, language modeling performance improves smoothly as we increase the model size, data set size, and amount of compute used for training. For optimal performance, all 3 factors must be scaled up in tandem. Empirical performance has a power law relationship with each individual factor when not bottlenecked by the other 2. So what this means is, if you're a hyperscaler, you look at your available data, compute, and GPUs, and you say, well, which one of these would bottleneck me? And then you pick the others based on that. So now you don't have to train extra. You can make a good bet. And that is kind of historic. And this is that history. So here's 2011, and here's 2022, and this is in log scale. So this is 10 to the 14th, this is 10 to the 25th floating point operations. This is how much it took to train a model. So let's just look at AlexNet. This is from 2012. So this model was 2 Fermi generation, 3 gigabyte NVIDIA GPUs, 2 GTX 580s, and this was trained in Alex Krzyzewski's bedroom. And that was the network that changed the world. Everything was different after this model came out. And then if you look, that's 2012. 2017, this is only about 10x more compute. Startups can still compete here in 2017 with the model that I just described. And here we are with GPT-4. That was trained at 7.5 megawatts for 90 days on 25,000 A100s. NVIDIA A100s. I did mention NVIDIA earlier. So this is not, if you take that model, a startup is not going to compete directly with that foundation model just because they don't have resources. The compute moat for OpenAI and hyperscalers is too big to cross. Or at least it's too big to cross until these models might be open sourced. So in 11 years, compute for a state-of-the-art model increased 7 orders of magnitude. That's 17.5 and that's 25.5. I might have even done that math wrong. So why are these scaling laws important on the business side? So Jennifer talked earlier about people on the data side needing to be able to talk to the business side, and I think this is one of the key places where these things interact. So these are other benchmarks. So this is the ImageNet. This is the queen mother of all the state-of-the-art results that people track. Look at how many those little gray dots are people trying to train a model to get the state-of-the-art performance. This is 2012, this is 2022, I think. This is iNaturalist. This is semantic segmentation on ADEK. This is question answering on Trivia QA. This is question answering on Wiki QA. And this is drug discovery on BindingDB. You don't have to know anything about these except that they all look different. And because they look different, as a business, you could never predict how well you were going to do compared to your competitors. So when I was at Deep Learning Analytics, we had an amazing team. Our talent really did come through on these kinds of benchmarks back when compute wasn't this huge differentiator. So this was always a risky bet, and it was a riskier bet if you didn't really trust that you had the best ML talent in the world. I did trust it. Look, there's Aaron right there. So this was one of the big business risks for ML in the past. But now, those scaling laws are a historic ML risk mitigator for hyperscalers. So now they can just look at their GPUs, their compute, and their data, and they can guess what LLM performance they can get with it. And that means they can just guess the other two based on the one that's going to limit them. So ML talent does still matter. It's super important because think about it this way. Do you want that millions of dollar investment in training a large language model to be left to maybe ML talent that you don't trust? No, it's super important that you get that right and that you don't do that multiple times. But the ML talent now for hyperscalers is less, I would argue, and we can talk about this in the Q&A, less about figuring out how to do it at all than figuring out how to do it right. Get the ML ops right, don't mess up. So now, what's next? So after Transformers, GPT-4, I predict more NVIDIA. So last time I talked was here in 2017, and since then, and I think at that point I said, hey, NVIDIA's doing really well. It went up 2x in the past, I forget how many months. But just this past summer, it went up $200 billion in a day. It's worth oh well, that's the end of that. It's worth 1.1 trillion now. So DC data community, you're welcome for this. That was the only stock chart I had the last time I spoke here. And NVIDIA also is named by MIT Technology Review as one of the smartest companies in the world. I agree, I respect MIT Tech Review's journalism. On the left here, people might know who Jensen Huang is. He's the CEO of NVIDIA. And the person on the right, does anyone know who? It's Ian Buck. It's right there. Anyway, so he is credited with creating CUDA. And CUDA is their middleware, the Compute Unified Device Architecture. That's what lets you do so. Jensen Huang started a graphics company to play games. And in 2006, he made an investment, and Ian Buck is credited with making it happen in CUDA, so that you could use these as inexpensive, high-performance compute engines. And we just saw that on the last slide, because almost all of those results were produced by NVIDIA graphics cards. And you can see that people are using them more, not less. And you can then also see that in the software tools that grow up around that CUDA environment. All of these accelerated frameworks use CUDA. So it's not like there weren't alternatives. There was OpenCL, and there were other FPGA-based approaches to train neural nets, but they didn't catch on. The software side really mattered. So I think more NVIDIA. I also think Llama 2 and its successors. So Llama 2 is just open source and it's commercially compatible, which means this is like Facebook making a $20 million investment in all the startups that use it. And Facebook is arguably helping them cross that compute moat that I mentioned earlier. Oh, I haven't been moving this forward, sorry. Oh, I'm on that, okay. So what I expect from that is a lot of startups doing really new and innovative things, because now it's not just the purview of hyperscalers like OpenAI, Google, Microsoft, But I expect both good and bad things, and I expect these to defy reductionisms as good or bad. The things that are going to come out are going to be both good and bad, socially, ethically, and performatively. So, one last bet before I take you on a brief journey. The most cited paper from 2023, I believe, is going to be this paper. This is that Llama 2 paper that just came out a few weeks ago that described the training that I mentioned. And it has a lot of authors, but I want to focus on Robert Stonek and Hugo Tuvron. Who are And I am going to tie this back to this room, this specific room, and people I've been introducing you to tonight, the alumni from Deep Learning Analytics, and Aaron's here in the front row. And this is, I'm not going to apologize for this. This is going to be more of a Charlie Kelly, thumbtacks and yarn version of how they're connected to you, but I will bring it back to this room. Just go with me. So, who is Robert Stonek? So he is the one that sold his company called Papers with Code to Facebook. And what's Papers with Code? It's this site on the left. So you can go through and look at 4,000 different tasks. These are ML use cases. And find a paper that says how they trained that model that got the best result in the world. In my opinion, that is the best ML recipe book in the world, and still is, even under Facebook. Are you going to get upset with me because I keep saying Facebook and not Meta? Okay.
It's fine.
So that's Papers with Code, and if you drill in there on image classification, that is that queen mother of all those ML tasks, the one that changed the world with ImageNet. And here you can see ImageNet approaching 90% accuracy. That's the site up there, Papers with Code on ImageNet. And you see top one performance is getting up to 90%. It started below 70%. And that is amazing. And like I said, you can click on any individual point in time and find the paper that says how they trained that. So if you then click on that, you look at it, it says it's fixing the train test resolution discrepancy, and lo and behold, there is Hugo Tuvron. Hugo Tuvron, not only do I think he's going to have the most cited paper in 2023, here he is in 2019 with the best result on the flagship ML benchmark, ImageNet. That's crazy. And when was that? That was May 2019. And what else was Hugo Tuvron doing in May 2019? He was submitting results to another competition. This is called iNaturalist. And there it is, I'm not kidding. It started in March 2019 and ended in June 2019. And he did all right. You can see his name down there. He came in 5th. That was Facebook. They came in 5th on the ImageNet 2019 result. And that's really good. But when you go to CVPR, they name the people that came in 1st, 2nd, and 3rd. And here in 1st is Meg V, that's a Chinese biometrics company. And then 2nd is Alibaba's machine learning lab. And then 3rd, oh, that's that company that I just sold to General Dynamics, Deep Learning Analytics. So here's another Deep Learning Analytics alumnus, Jeremy Trammell, beating Facebook at a 12-person startup. And actually, he's beating all of North America, right? Because the top 2 entrants are Chinese. Oh, but what about in 2018? Who was at the top of the leaderboard in 2018? Oh, it's Deep Learning Analytics again. It's 2nd. And the only team that beat us was Dalian Institute Technology. That's basically China's Caltech. And oh, the third place team, it's worth mentioning, that Fadivu Gibbs, that was Baidu. That's China's Google. So, and again, a 12-person startup was beating Facebook and Baidu at international machine learning competitions. And let's also recognize Priya Oberoi. She was part of that team in 2018. So respect to her too. Where are we then? So then, who visited the company? So these are those people that I've been introducing you to. There's Pri, there's Professor Eggenreiter, because he was part of that iNaturalist team. There's Dr. Sleeman, who I mentioned earlier. This is Paige, who pointed me at that media cloud site. There's Aaron, he's down here. Jeremy, I'm sorry my head's in the way, but there is a picture of him there. There's Danita, who helped with that legend. And does anybody know who that is in green? Does anybody know? No?
Don Byer.
Oh, who said that? Who said that? All right. That is Don Byer visiting Deep Learning Analytics in 2019. And that's the district you're sitting in. And I'm not kidding, that is Don Byer. He is former Lieutenant Governor of Virginia and former Ambassador to Switzerland and Liechtenstein. But that's not the crazy part. The crazy part is, here is a story from our local paper, and our local paper is the Washington Post, saying a 72-year-old congressman goes back to school pursuing a degree in AI, and if you ask the author of that article, why did they go back? They said intrigue. Her name is Megan Flynn, and she writes, a few years ago, Byer visited an AI company in Arlington that had just performed well in an international machine learning competition. That was deep learning analytics. And I did not charge a finder's fee to George Mason. And what's that got to do with you? He just met those deep learning analytics alumni, just like you did. And he visited George Mason's Innovation Center right here. And that's where you're all sitting. So QED, I told you I'd bring it back to this. So that's the story. Now, links. These are the links if you actually want to get the links to click on before I get this to you in some version that's bits. Okay. This talk was never intended to be a standalone talk on Transformers. There's a lot more that's happened since 2017. And this is my ask to you all to talk to everybody about the more interesting things. This was honestly, God, the thankless work. That nobody wants to listen to anybody talk about position encoding or things. And my apologies for that, but thank you all for your patience. What people do want to hear about are things like how to beat ChatGPT using open source LLMs and transfer learning. So Prima, could you stand up and just wave to the crowd? So Prima's going to be talking about that sometime in the near future. Watch for those October talks here. And that's through this meetup. What used to be DataOps DC is now called DC Generative AI. It was on the original slides. But also there are lots of other things that are interesting, like retrieval augmented generation, low rank adaptation, just Llama 2 versus ChatGPT. There are legitimate reasons that you might want to use ChatGPT. Fine tuning, anything that uses maybe Hugging Face's environment, Argilla, for curating an instruction data set to fine tune these things. All those are really interesting to this community, and I think super important for the startups especially. So, Q&A. So before we do Q&A, I want to do something. So in large language models, there's something called in-context learning. And so what you do in in-context learning is you give a bunch of pairs of things. Like you say, I don't know, I didn't think of an example, but you give it examples of like fruit, orange, vegetable, pick a vegetable. What's a good vegetable?
Cucumber.
Broccoli.
Broccoli. And then you say cat, and then it should say, I don't know what it would say. The point is you give it examples, and then it figures out, based on the relationships between the first few things, what might be useful. So here are some questions. The first question, should you be intimidated by LLMs? You should not. Are LLMs magic? They're not. Are LLMs artificial general intelligence, AGI? They are not. No, really, they are not. They're still not, and this discussion is distracting from more productive discussions, especially ethical ones. If foundation LLMs are so expensive to train, will I ever do that? I did say it, but no, you probably won't. Was there a bug in the original transform diagram? Yes, there was, and aren't you a key nose to detail? And yes, you put the normalization inside the residual blocks, and there's more to read. Read that paper there. Why would they add a position perturbation? Why not just augment the vector? Also a good question. Read the diverter paper. And thank you for your attention. Thank you.
Okay, fine.
Are there questions? I can't believe you still want me to talk.
Questions out.
In the back there, and sorry for spilling on you last data tricks.
So I've got a question about how is there any work that's currently being done that focuses on making sure that the order in which a model is trained, different examples, doesn't affect the result of the model, and if so, how effective are these models compared to current state of the art? Because many models have accuracy around what they end up getting some data that they trained earlier.
Okay, so let me see if I got the question, and I'll repeat it for the audience. I think the question is, what work is being done on the sequence in which examples are provided to the model for training, and does that matter? That was one question, and was there another one?
No, that was basically it.
Okay.
Early models are like computed.
I would refer that question to the woman sitting behind you, also a deep learning analytics analyst, Dr. Jennifer Sleeman. She hates when I say her name in public. I don't know. Jen, do you have thoughts on that? What kind? Dynamic neural networks that apparently pay attention to the sequence in which things are observed. So you can also read that question a different way, and that is when LLMs specifically respond to a prompt, there is some sensitivity to where in the prompt relevant information comes from that it'll give you a response. And what people have seen is both information at the beginning of a prompt tends to be overrepresented in outputs, and information at the end of a prompt also ends up being, and it kind of has a hard time finding things that might have been in the middle of the prompt, for instance. And that's relevant for RAG applications and other applications. But thank you, Dr. Sleeman, for the dynamic neural net. Can you share with the class? Yeah, in fine tuning, it really might pay a lot more attention to the last thing that you showed it. Okay, so up front, Elliot.
Thanks for do you see trends either in architecture or chip design that are causing some of these large language models that are too expensive to train for startups to be more accessible, either like chips that can become more powerful, or for like architectures that can replicate those of larger models but don't require the same compute resources?
So, that's difficult. I would say the compute is typically going to be matched to your use case, and it all depends on what your use case is. So it's hard to give me it's hard for me to give you a general answer, but there is a startup called Useful Sensors by Pete Warden. He was the person that originally sold Jetpack to Google, and he uses these very, very tiny compute platforms for things like wake words and just counting people, etc. So you can go really, really small and run those on like watch batteries. But then there's also in the middle, like NVIDIA has their Jetson architecture, and that's made for computation at the edge for bigger workloads. So there is a spectrum to how much compute you need So is hardware being developed there? I would say yes, based on what I just answered. I don't know if I can, does anybody else have something more to add to that, this whole spectrum of compute on ML use cases? All right, well, is that enough, Elliot?
Can we take this to the bar?
Oh, someone wants to take this to the bar.
Yeah.
I would like to take the bar, but I would also, I think I'll get through some.
Let's do one more question just so people can.
All right.
We're at 8:40 right now, so one last question.
Go. Yeah.
Generally, you've given a detailed description of how transformers work. But in reading papers in general on the different types of LLMs and architectures, we don't get an insight to the formulas and calculations that are just generalized. How do you find the actual formulas? Because I'm interested to see where you get that information.
So the question sounds to me like, hey, when we read these papers, we don't get these formulas. And how did you go? It was a lot of scouring, and also I really wanted to focus on visuals that would be accessible to a broad audience, because it's not everybody's at the same level of expertise here. So it took a lot of work.
Thank you.
Like personally speaking to people who work.
I talked to people, but mostly I read, and like I said, I've been doing this for 30 years, so that helps.
We've got one last question, I think, here from Will.
So Will, one last question actually from the YouTube live stream. Question from George, who also said, that was a great presentation. George's question is, will the PowerPoint be available after the presentation?
Some version of this will come out, yes.
We will post it on the meetup.
All right, I guess we'll talk at liberty. So thank you all for your attention.